glad to introduce Dan Povey, who graduated from Peterhouse in Cambridge 2 years back, something like that. Yeah. And he's joined IBM research. He mainly works on acoustic modeling, and he's responsible for the big margins of victory that both Cambridge and IBM had in recent years in the LVCSR evaluations. So, without further ado.
I'm concerned that after Zach has hyped me up so much, I'm not really going to be able to fulfill any expectation. Okay, so this, let's try to get it on the big one. This is only going to be a very high-level talk. I'm not going to, I thought since not everyone here is really interested in the details of discriminative training, I'll just give you an overview of what it's all about and describe the various techniques. I'm going to talk about MMI. Initially I was doing work on MMI, which is a form of discriminative training. I'm going to talk about MCE mainly as a contrast, because that's the other major technique that people use. And then talk about these new techniques that I've been working on. Just for those of you who aren't really into acoustic modeling, in speech we train these hidden Markov models on these vectors. You know, we have a sequence of vectors every time. And these hidden Markov models, they have means and variances because we train Gaussian distributions to model them. And normally you just estimate them statistically, where the mean is, you know, the average of whatever it's supposed to be the mean of. But it's possible to get better recognition performance by estimating the means and variances to optimize the accuracy on the training data. So to basically run the model on the training data and try to make it more accurate. Two of the ways that people have done a lot of work on are MMI and maximum mutual information. Forget the name because it's kind of irrelevant to what it is. And minimum classification error, MCE. I also, while I was at Cambridge, I introduced fMPE, which is a technique that shares some of the properties of both, and I think is more suitable for large vocabulary stuff. And I'll also talk about something more recent, fMPE, which is discriminative training, but in the feature space, and I'll explain what that means. MMI is a training technique in which you try to maximize the posterior likelihood of the correct transcription. So basically what you're doing is you're recognizing all the training data and looking at the probabilities of all the possible transcriptions for that utterance and trying to maximize the probability of the correct one. By the way, I have to apologize that I've prepared a talk without pictures or equations because, well, for time reasons. But hopefully most of you wouldn't have appreciated the equations, and the pictures are just for show anyway, so we'll have to let it go. From a computational point of view, MMI involves decoding all the training data and preferably getting some kind of lattice or n-best list out. So it's computationally a little bit expensive. All discriminative training techniques are. I think it was originally developed at IBM by Dmitry Kanevsky, but only for discrete HMMs, which is something nobody uses anymore. It's where you have you do this vector quantization on the acoustic data. It was extended for continuous Gaussians, which is what we use, by this guy who's working in Canada called Yves Normandin. And it was applied in Cambridge to large vocabulary speech recognition, which just, I think that was an implementation issue really. They got their lattices working on it and stuff. And I picked it up from where they started, and I messed around with the update equations to make it more robust and work better on large vocabulary. They had this rather strange update equation in which you estimate the mean by, you have this numerator statistics, and it was the numerator minus the denominator plus this constant term called d. And because of the way it was derived by Dmitry Kanevsky, this d was just this constant factor that disregarded how much data you had for the two Gaussians. And although I can't really describe it to you now, it was just totally dimensionally wrong. And I just fixed the dimensional problem by multiplying it by the occupancy, and it worked much better. But something I wonder is, why did no one see this problem before? Did people not check that something makes dimensional sense? This is a very general point, but I think in statistical stuff, people rely a lot too much on formal proofs of whether something is correct, and a lot too little on just simply sizing something up and say, is this about the right quantity? Is it too big? Is it too small? Anyway, so I just fiddled around with the MMI trading split procedure, and we started using it.
So you're saying that choosing D out of the hat works less well than, say, choosing D as some constant times the frequency. That's what you're saying.
Yeah.
Or there are more funky ways you choose.
Yeah. Well, I mean, the reason D was set to this constant originally was to do with this proof he had of it, and I don't know. It's a big issue and a very technical one, which I don't really want to get into. I was just saying that I think it's like the whole SVM thing that I was talking about earlier. People get, this is a wonderful proof. No one really understands the proof, but the proof is very important, and they just disregard all intuition. That's my feeling. Okay, so the general discriminative trading process is you have to have a decoder to decode all your acoustic data with lattices, to get lattices out. And then you just do that once. And then for several iterations of training, like 4, say, you accumulate 2 sets of statistics from the data. One is the statistics you normally get when you're doing estimation maximization. It's, for every Gaussian you have a mean statistic and a variance statistic. And you have that normal one, and you also have one for the recognized data. So you have your correct transcription statistics and your all possible transcription statistics, and the update is of the form 1 minus the other. So you want to maximize one and minimize the other. I'm kind of regretting I didn't put the equations down, but I don't know what level people. No. Well, I don't know what most people here know about speech recognition.
I think most of us have seen the equation. We know what you're talking about. For example, for means you have made gamma O for the numerator, and then you have certain thing.
Yeah, it's. I don't know. I'm still not sure whether people need to know stuff at this level of detail. But say x is. Let's say that this means that the sum of the sum over all the training data of the x value that aligns to that Gaussian, and sum of x squared is the sum of squares. In the normal update, you just set the mu is sum of x over count, and in the extended Baum-Welch update, it's something like mu is sum of x for the numerator. This is the same as this. This is the correct transcription mean, and then minus the sum of x for the denominator. This is the mean that you get if you say that the transcription can be anything you want, and I'll leave it as a slack variable and sum over everything. So this is from the correct transcription. This is from what you would get if you recognize, and this could be wrong. You just subtract them and have, c num minus c den. And then because this could be negative and this could be negative, you don't want to divide by a negative number, you add some constant. And I was really just messing around with that constant because it's obvious that it has to be of the same magnitude as these, as well as these counts at least. And it seems insane to say set this for 1,000 when these counts could be either, there could be 10,000 or there could be 2. It just gives you totally inappropriate learning rate. And yeah. So, and something else I was looking at was the acoustic scaling I messed around with. Because you have this language model scale. Obviously that thing is a real probability. So I started scaling the other way, scaling the acoustics instead of a language model, which puts more weight on the less probable denominator utterances and gives you a kind of smoother estimate. Anyway, so we started using MMI, and a lot of other groups started using it too. This is just a slide about how useful is MMI. I think the main hurdle has probably been the lattice generation. You say you have lattice generation. I guess this AT&T decoder, they released the decoder then?
You can have the binary.
Oh, the binary. I see. Yeah. So generally you can get maybe 10 to 20% improvement relative in word error rate, depending on the setup. But you get more improvement when you've got a lot of training data relative to the number of Gaussians. So in Cambridge, we always tended to use a small system. We had quite large improvements. Also, we often tested it before VTLN and SAT, and that gives you more improvement too. Yeah, so I think all of these groups are doing it to some extent. IBM, I think Panasonic, and Microsoft and BBM. And I think you guys have started looking at it too. This is just for contrast, really. The other main discriminative training technique that people have tended to use is MCE. I think it was invented by some guys at AT&T who are probably no longer there. I said it maximizes the differential approximation to the question, is this utterance correctly transcribed or not? They actually maximize this objective function that's really very complicated. It's a sum over all of the transcriptions of, you take the correct transcriptions log likelihood, and then you take the kind of soft max log likelihood of all the other transcriptions. And then you take the difference and put the difference through the sigmoid. So the equation is enormously long to write down of what it actually is. But I've always believed that it's totally inappropriate for a large vocabulary speech because, well, it's very sensitive to how you segment the data because basically if you've got an utterance and you've got your correct transcription, say the cat, and and let's say the hat is the most probable competitor. Depending on the difference in likelihood between these two, let's say the difference in likelihood is here 0 is they're the same. You have the sigmoid function, and only if they're about the same will it have any gradient. Otherwise, it'll be 0. But then let's suppose we have a longer utterance. The cat something, and these two things are totally different, and the wrong one is many times more likely than the other one. It'll push the if you then look at it for this whole utterance, it'll push the sigmoid, over to this point, where it has no gradient at all. So the fact that you consider more of the utterance means that it ignores this error now. And in fact, someone told me, I don't know if people ever published this, but someone told me at ICASP recently that they don't bother using the sigmoid for continuous speech recognition, which I think is rather scandalous that they would do that and not say anything about it in the publications. But maybe they have said it. Anyway, it's mainly for some reason in Japan and Hong Kong that they use this. And they're always working on like Japanese aurora digits or something, which none of us use, so it's difficult to tell whether it really works. And personally, I never bothered because I started looking at it and then I just said, forget it, it's not going to work. So maybe that's not very scientific, but you have to have some prior beliefs. Well, I mean, if someone else thinks it works, then it's their responsibility to try it on some respectable task. That's my point of view. It's the same with any technique. Okay. MPE is a discriminative training objective function that I developed at Cambridge. It uses. It's again something for which you have to consider all transcriptions, all possible transcriptions of an utterance. And it uses the concept of a phone accuracy, which is the number of correct minus the number of inserted phones when you look at the alignment to the correct transcript. Some people have questioned the accuracy of this formula, but that is actually the formula that you use to calculate word error rate, if you think about it. So the objective function is for each training utterance, the average overall sentences, but weighted by the posterior probability of that sentence, of this phone accuracy. And the reason that's differentiable is because the likelihood of each sentence can change depending on the acoustic parameters. So Well, in terms of the algorithm, this comes down to almost the same computation as MMI. So there's one extra little stage. I use the same extended Baum-Welch update formula as MMI. So from an implementation point of view, they're really quite similar. But something important which I have to mention about MPE. If you just implement the vanilla MPE, it won't work. It will give you great performance on the training data, but not so well on the test data. What you have to do is this thing called eye smoothing, in which if you have, once you get fewer than about 50 parameters, 50 counts for these numerator and denominator things, you start smoothing off back to the ML estimate. So it's a little bit like the smoothing you do in language model estimation. It's just something that has a tau value, like when you do map estimation. You add 100 counts of the ML to whatever you were going to use. And it's, I think it's possible to formulate as some kind of Gaussian prior. And it's enormously important to actually work on the test data. In terms of utility, as I said, it's easier to implement once you have MMI. A slight difference is that you need to have lattices with phone markings in order to calculate this phone error. In Cambridge we had that already, but it's not clear that anyone else would necessarily have it. It mostly gives improvements in word error rate over MMI, but that's not totally consistent. In IBM, I initially found that it helped when I implemented it there, but then later on for another task, for another test set or something, it didn't help. But what I've started doing and what other people are doing now is this eye smoothing. You can eye smooth using the MMI estimated mean invariance instead of the ML estimated mean invariance. And it turns out that for some reason the MMI estimated one is more robust than the MPE one. So you get an estimate that's both robust and good. This is just a technical detail that you'd have to know if you wanted to implement it. Some people have just tried alternating MMI and MPE on different iterations. And in the LVCSI community, quite a lot of people can do MPE. I don't know how many of us are really doing it as a routine. IBM and Cambridge definitely do it as a routine. I know that BBN do it sometimes, but I know it doesn't go always. And I don't know what Microsoft do because they are really participating right now. Okay, fMPE is what I've been working on in the last couple of years at IBM, and it's a feature-space version of discriminative training. You're training a non-linear offset to the features. Say the features are x of t on the current time frame. You get h of t, which is got by, you take, say, 100,000 Gaussians, and you find the posteriors of those Gaussians given the frame xt, just by evaluating them all and dividing by the sum. Then you have a very big sparse vector that's like 100,000 big, and there's one or two non-zero elements in it. And you're going to multiply that vector by a matrix M, which is going to be trained. So it's basically a question of we're going to train M. And it's trained with just linear techniques. Obviously, you could never use like matrix-based techniques for training something like that. It's all really based on differentiation. You differentiate the MPE objective function with respect to these matrix parameters. The matrix starts off as 0, so that your features are just whatever features you had before. And then on each iteration, you update the matrix parameters. And there's a few, to get it to work, there's a few little details like you've got to get the right learning rate for each matrix element, and so you've got to size up how sensitive things are to that matrix element. And I do that by dividing by the sum of the positive and negative contributions to the differential. And I use something which I call the indirect differential, which is, the idea is when you differentiate with respect to n, you don't assume the model is fixed. You assume that the model will change as n changes. Because obviously, if a particular mean gets a contribution from a certain vector, as the vector changes, it'll change the mean a little bit too. And the mean itself, as the mean changes, all the probabilities will change for all the different transcriptions. And that'll change the MPE objective function. So you can differentiate backwards through that process and work out this indirect differential, indirect contribution to the differential. And it's important to do that if you want to do ML training after. The reason this kind of term doesn't arise in a lot of optimization problems is that you're usually training the two different things with the same objective function. It turns out not to matter in that case. Like if you're doing feature space MLLR, CMLLR, you're training both the means and the MLLR transform with the ML objective function. And it turns out that you can ignore the kind of indirect effects in that case.
So what you're saying is that if I vary, let's say, the ijth element of m,
Yeah.
what that's going to do to my likelihood is that it's going to change the value of y, because
Yeah.
obviously it changes.
Yeah,
And I can compute the change in the total likelihood because y has changed.
that's right.
But at the same time, because y has changed, if I were going to do an ML estimate of all the Gaussians,
Yeah. The Gaussians would change
all the
too.
Gaussian means would change.
Yeah.
As a result, all the posterior properties
Yeah.
which H encodes change.
Yeah.
So there is an M-dependent component inside H.
Yeah. Inside, wait.
So let's say little mij is the ijth component.
No, it's not inside H. The Gaussians that you use to evaluate HT are just fixed.
Okay, those are fixed.
They're fixed. They're
Those are
not the same as the Gaussians in the HMM set. But the reason you get this indirect term, it comes from the acoustic model, because the means and variances will change everything. It's just differentiation, really.
Okay.
Yeah.
Okay. In other words, not only will y of t change, but because y of t changes, you will change
The model parameters will change.
the model parameters.
I mean, initially I wasn't using that, and I found that it worked okay, but the problem is if you then did ML training on that data, it got worse again. And if you want to do discriminative training afterwards, you're in effect going to be doing ML training because you have this backing off with eye smoothing and so on. And I just think it's bad not to be able to train on the parameters, because then you can't do extra stuff on top of it. You can't do MLLR. It's not an ML trainable system. It just seems like a bad thing to me. So, yeah, I mean, it gave us quite respectable improvements. I think maybe in the region of 10% to 15%. The results we got in the last switchboard evaluation were perhaps not the best results because I've improved the setup since then. I'm going to describe exactly how in my next Eurospeech paper, but yeah. I think you can expect 10 to 15% relative improvement, sometimes quite a bit more on very small tasks. It isn't quite as convenient as discriminative training because you have to do some computation in test time. But in the latest setup, that can be very small, like 0.05 times RT, or maybe 0.01 times RT. I'm sure it's possible to improve it by... Okay, I think these extra details I've mainly mentioned already. Oh yeah, I didn't mention the context. This high-dimensional vector HT, in order to get some acoustic context, I actually splice it together across a few frames. And I also splice in a few averages of frames as you get further out. That's all described in the paper. I mean, it's probably not the level of detail that you really need to know. Okay, this is just references. I think my thesis is the most useful reference for work on MMI and fMPE. And the fMPE stuff, there's an ICAST 2005 paper, and there's going to be a Eurospeech paper. Okay. This is on a kind of less specific and less technical subject. I discussed this, I think, with the language modeling people already. It's just a hypothetical question, really. If at some point we solve the speech recognition problem, what will the answer look like? I don't believe that we're going to have a little short answer. Someone's going to say, oh, you just have to have e to the x and divide by I and then multiply by the training data, and that's going to be the answer. I think it's pretty clear that you're not going to have such an answer. So I think we've got to just resign ourselves to the fact that nobody is going to suddenly discover the answer to speech recognition, and we're going to have to just get some kind of infrastructure that makes it possible to deal with very complex solutions. I'm thinking of maybe some description language in which you have all of these different components of the problem which have some normalized interface which you could somehow describe. Does anyone have any comments on this at this point?
Well, some of us are working on this.
Really? I doubt that it's going to be the same as the solution that we would need. What are you talking? Is this for language?
We can talk about it outside the talk, but if you're...
No, this was intended for discussion. That's the point of this slide.
That's a great slide.
Yes. I think the more you think about it, the more difficult it is to work out what that language should look like. Because if it's just some kind of procedural thing, like, I don't know. There's a difficult trade-off between generality and being useful.
Well, if you want a counterpoint, my counterpoint is that no, I think when we're all done, it will actually be a fairly simple solution.
You think so?
Because what it will say is it will essentially say that the speech signal carries a whole lot of information, which has nothing to do with the words in it. And if you're interested in the word in it, this is what you do to the signal to get rid of all that other stuff. I don't need to know whether the person's female. I don't need to know whether they have a high pitch or a low pitch voice. I don't need to know whether there is a reverberant or a quiet room.
But what you're saying doesn't really tell us how to do that, does it?
No, that's
But
what
you think that someone is going to come up?
Say,
I don't know.
this is all the extraneous part of the signal. Get rid of it, and what's left?
I just don't believe there'll be a magic bullet. If you look at the human brain, my understanding is, I think Steven Pinker's book is very good. Scientists believe that there are pretty much different modules for every different kind of learning task that our brains have, and that the language module say is separate from the vision module, separate from the smell module, separate from the coordination module. And I mean, the fact that we have to have all these different centers that have different setups for different problems shows, well, it makes me think, which is something I thought already, which was that there's no general learning solution. Each solution has to be specific to the problem. And that means that you wouldn't think that there would be some nice formula which would work for speech, and then some other nice formula which would work for vision, would you? And some other nice formula which would work for smell. I mean, if they're going to be different, I think they're going to have to be messy.
Yeah, nobody said it's not going to be messy. What I'm saying is, when applied, what comes out of it will be a simple transformation of the speech, recognizing it.
But isn't that just trivially true? Because anything you can say is a transformation.
What I'm saying is that it doesn't have to be a complicated system. Part of the reason it's complicated right now is we are not accounting for all the other things that think of them as confounding variables. To recognize speech in spite of them rather than by taking them cognizance. I don't know.
I suppose it comes down to a question of belief.
Well, the question is whether, Sanjay may only be talking about the part that corresponds to E equals MC squared, which doesn't tell you how to build a nuclear reactor. I mean, a lot of the reason that these things are complicated is that the description of what you're trying to do is considerably shorter than the description of how to actually do training and decoding.
I see what you mean.
So,
yeah, I suppose it's intuitively obvious what we want to do when we write down speech, but I suppose it would be difficult to write it down in any formal language. I don't know. Maybe that.
Yeah, so that was one part about whether the solution was reality. So sure, you would need to make uranium hexafluoride and spin it around and purify it, and only then will E equal MC squared help you. So maybe the rest of it is just engineering, and that's what we do.
I don't know. I really don't think that analogy holds, because at least the natural world can often be described by quite simple mathematical formulas, like velocity rises as the square root of energy or whatever.
Only if it's an extent.
Yeah, but
I mean, are you saying that the human brain has all these complex modules that something's going to get hijacked to do reasoning? The human brain evolved.
maybe we have a reasoning module.
I don't know if there's any reason to think that. It's like language got hijacked.
I don't understand what you're saying. Can you try again?
So you're arguing against the perhaps old-style AI architecture where you have planning and and search as separate modules that are
Oh.
on top of various feature spaces. Is that correct?
I actually really wasn't trying to make a general point about how to build AI. I mean, this is, I believe AI is just so impossible and way off that we should forget about it. I'm just thinking in terms of the speech problem. Just in terms of decoding speech, we're not going to be able to, not going to find some simple solution. So we might as well just look for ways to deal with complexity. And look, let's suppose there's some solution out there. The process from getting here to there is really a question of search. So I think we should look at it as a search problem and say, how do we make it easier to move things about, to change modules, yeah. But rather than just say we need to be geniuses or we need to think very hard. We're not going to, the answer isn't like that. That's my view. Oh yeah, and I was thinking, this is a subject that we always argue about at IBM. Does anyone know Stan Chen? Stan Chen is a great believer in AI. He believes that one day robots will be smarter than humans, which I just think is totally nonsense because we all work in AI and we know that how difficult it is to get things to work. I think it's related to this whole question because I think the difficulty of speech and the difficulty of AI are part of the same difficulty.
So that part I believe, that speech in some sense is AI complete. I don't know who used that phrase first, but it's still used. If you could do perfect speech recognition, you would do perfect.
Yeah, well, I suppose maybe that means we'll never do perfect speech recognition.
That means we'll have jobs for a long time.
Well,
But without filming.
yeah. So perhaps we should wrap it up. I don't know how long I've gone, but I think these things should be kept short in general because one can waste so much. No. I don't really. No, I don't have any extra stuff. This is the last of what I've got.
Do you want to say any more about? Sorry, I'm not forgetting.
MPE.
MPE, sorry.
Well, I don't know. I think maybe it's better if I talk to individual people who are looking at that kind of stuff, because I really, clearly the technical details of that are not so relevant to those of you who are working in language modeling or in other stuff. And you can always email me. Yeah. Sometimes people come to me at conferences and they say, "Oh, we tried MPE and this happened." I said, "Why didn't you ask me about this? Because it's usually some very simple problem. They got some scaling factor wrong or something." Yes. Yeah. Let's take this offline unless there's anything else very specific.
I have a question about the fMPE. You mentioned that the HT vector contains the posteriors from some Gaussians.
Well, that's the HT. I mean,
Yes,
XT
the
is the yeah.
So you mentioned that this Gaussian this Gaussian will come from the HMM model that you have.
Yeah. Well,
So how do you?
I actually got them by clustering the Gaussians using a likelihood-based clustering, which is actually computationally difficult unless you speed it up somehow. But there's other ways to do it. I actually tried training them from random vectors, just training them with type variates and then no type variates at the last iteration. And that gave slightly worse performance than the clustered one, but it wasn't very enormous.
So at each iteration, do you have to update this?
No, they're fixed.
Okay.
Yes.
I guess MPE is done on this supervised learning with you know the reference.
Oh yeah.
Yes. So in the case when you don't know the reference,
I'm very skeptical that could ever work. Some people have tried, MPE-based MLLR and stuff like that in an unsupervised framework, but I'm very skeptical that that's a good idea.
So you think it's dangerous to use the hypothesis as reference?
Yeah, well, the whole point of discriminative training is that you try to upweight some hypotheses and downweight others, and unless you know which ones are better, I think it's very difficult to do that. I mean, maybe you could try with a very strong language model and then build an hypothesis with a very weak language model or something. Mm-hmm.
Maybe you covered this in some generic comments about generalized probabilistic descent, but how is it also seems similar to deterministic annealing, only you're taking one weighting between the prior and the model.
Yeah, I suppose. I mean, I don't view it as a way to improve the optimization process. I view it as a way to. I'm talking about this eye smoothing.
Yeah.
Yeah, I view it as a way to just get a more robust estimate, because if you don't use the eye smoothing, you get better performance on the training data, but worse on the test data. So I think it's pretty clearly an issue of generalizing. Yeah. Hmm. Yeah, okay, let's go, because I always, I don't usually go to these kinds of talks at IBM because it just takes so much out of the day. That's my, I don't know. Thing is, because we have like twice a week or 3 times a week some seminar, and it's usually in some totally irrelevant subject, and if you go, it's a whole hour out of the day, which you know.
We do it once a week.
Okay, thanks. Okay, finito. Let's.